JavaScript numbers that contain a fractional part smaller than 1 are inherently imprecise. You might expect that adding 0.1 to 0.2 should result in exactly 0.3, but the answer that we get is off by a very small amount. I won't go into the technical details of how numbers are encoded, but the non-technical explanation for the imprecision is that some trade-offs were made to sacrifice a small amount of precision in exchange for speed and less memory required to store numbers. Many sources state that the precision is between 15 and 17 decimal places, but the reality is that the precision varies and is less as the numbers get further away from 0. In these two examples, I add 0.2 and subtract the expected result. This yields the size of the error. Using a larger number results in a larger amount of error. For most normal math outside of science, pure mathematics, and finance, the imprecision is not very important and we can just ignore the extra decimal places. If you want to show a number with fewer decimal places, you can use to-fixed. Parentheses are used for the addition so that the to-fixed is applied to the result of the calculation instead of applying it only to the 0.2. The to-fixed takes an additional number inside its own parentheses to specify the number of decimal places. It is possible to use to-fixed on an expression surrounded by parentheses, directly on a number, or on a variable that holds a number. Doing it directly on a number is not common because you could just write the number with fewer decimal places. Using to-fixed does not simply truncate the number, it rounds to the nearest number that has the specified number of decimal places. Note that to-fixed can only be used on a number. If you try to use it on a string that holds a number, that string will not be coerced into a number. You will just get an error instead. One other important detail about using to-fixed is that it outputs a string and not a number. We can verify this by using type of. When this keyword is placed in front of a value, it returns the type of that value. This output shows that x is a number, but y is a string. A related operation that you might sometimes want to perform on a number is setting its length. This is primarily useful when you want to fit the number into a fixed amount of space like on the display of a calculator. This is done using to-precision. Note that to-precision also rounds instead of simply truncating the number. Using to-fixed specifies the number of digits after the decimal, and using to-precision specifies the total number of digits. Note that both of these can only be used on numbers that actually have a decimal in them. It doesn't make much sense to use them on whole numbers anyway, but if you really wanted to, you would need to add an extra 0.0 to the numbers to make this work. If you want to round to a whole number, JavaScript offers several options. Math.round is used to round numbers to the nearest whole number. If the decimal part is less than 0.5, it rounds down, and if the decimal part is greater than 0.5, it rounds up. For exactly 0.5, it always rounds up. This can be surprising for negative values since it is more common to round away from 0. Notice that the number must be placed in between the parentheses that follow math.round. This also works with variables, and it can also be used with expressions. If you always want to round down regardless of the value of the decimal portion of the number, you can use Math.floor. Notice that this outputs 3 even when the value used is very close to 4. If you want the opposite effect of always rounding up, you can use Math.ceil, which is short for ceiling. Notice that the output is 4 even when the number is very close to 3. Note that rounding a number is different from truncating it. If you want to discard the decimal portion of a number, you can use math.trunc. The trunc is short for truncate. When used with positive numbers, the result is the same as Math.floor, but there is a difference when used with negative numbers. Math.floor rounds down to the nearest whole number, so doing that to negative 4.3 results in negative 5. Truncating the number produces negative 4 instead. Some programming languages have a special number type that retains precision while allowing for a decimal in the number, but JavaScript does not have this. One trick to get around this when working with currency is to encode all values in cents instead of dollars. For example, $5.25 would be encoded as 525 cents, allowing the number to stay whole. When adding, subtracting, and multiplying by whole numbers, the result maintains precision. Some precision is lost if there is a tax or interest calculation at the end, but that happens only once. Using dollar values would result in accumulated errors that happen on every addition or subtraction. Because the inaccurate computations only happen a few times at the end, the final result has an inaccuracy far less than 1 cent, and to fixed can be used to remove the extra decimal places where the inaccurate information is held. Whole numbers can become imprecise if they are very large or very small. There are two predefined constants for the maximum and minimum whole numbers that can be represented without loss of precision. These are referred to as safe integers. It is possible to represent numbers outside of this range, but unexpected results can occur. This code shows that adding 1 to the maximum safe integer produces the same value as adding 2 to it. This doesn't mean higher numbers can't be encoded, they're just not precise. For example, it is possible to multiply the maximum safe integer by 2 and it will produce a higher number, which is actually the correct value in this case. However, you can't trust all math with such high numbers to always produce the correct output. If you need to use numbers outside the safe integer range, you can use big integers. A big integer is written like a normal number followed by the letter n. This code shows a comparison between regular numbers and big integers when going past the maximum safe integer. The regular numbers produce an incorrect result, but the big integers produce the correct result. Despite this advantage, big integers should not be used as a general purpose replacement for regular numbers. As the name implies, big integers can only be used for whole numbers. Decimals cannot be used with big integer values. Performing calculations with big integers is also slower, and it is not possible to mix regular numbers with big integers in a calculation without explicit conversion, which makes the code more verbose. For a literal value, adding the letter n is sufficient, but converting a variable requires adding big int before the variable name and surrounding it with parentheses. This approach also works if the variable holds a number in string form. If you need to convert a big integer back into a regular number, you can use similar syntax but using number before the parentheses instead. Note that this should not be done with numbers that are outside the safe integer range if you want an accurate result. And the only reason to use big integers is if you expect to have values outside of this range, so this conversion is not common. Doing the conversion on this specific number produces a value that is 1 higher than what it should be. If you're willing to tolerate a bit of imprecision and choose to use regular numbers instead of big integers, you may sometimes encounter that your numbers are displayed with the letter e. This is scientific notation, and the e is short for exponent. It does not represent the base of natural logarithms, which is normally represented by the letter e in mathematics. It instead refers to the number 10 raised to a power specified by whatever value comes after the letter e. The number before the e is multiplied by the result of the exponentiation. So 1e plus 22 is equal to 1 multiplied by the result of 10 raised to the 22nd power. If the e is followed by a minus sign, this indicates that the exponent is negative. You don't need to have much understanding of exponents to work with numbers that have e in them, because powers of 10 are simpler than other exponents. 10 raised to any positive exponent whole value is equal to 1 followed by the number of zeros specified by the exponent. For example, 10 raised to the third power is 1 followed by 3 zeros, which is 1,000. So 1e plus 3 is equal to 1,000. For 10 raised to a negative whole exponent, start with a decimal point and add zeros until you have 1 less than the exponent value. Place a 1 after the last zero. For example, 10 raised to the negative third power is 0.001. The e will usually not appear in a number like 1,000, but it can appear when using to precision. Note that the extra 0.0 was needed because to precision can only be used on numbers that have a decimal. We have covered most of what you would need for regular math in JavaScript except for the trigonometric and logarithmic functions. We will not be covering those in detail because figuring out how to use them is quite simple once you understand how to use functions. The next topic we will cover is creating and using functions.